Maintaining a stable environment for 5,000 concurrent Omnissa Horizon virtual desktops requires precision engineering at every layer of the stack. In a multi-site, active-active data center deployment, the compute hardware rarely triggers a systemic failure. Modern servers can handle dense processing loads. The true choke point emerges lower in the stack. When thousands of virtual machines execute concurrent read and write commands, the network underlay must process massive volumes of east-west traffic, server-to-server communication, entirely contained within the data center. If you run user-facing virtual desktop traffic over the same congested pathways as hyper-converged storage replication, the packets collide. The storage operations consume the bandwidth, resulting in immediate latency spikes and dropped user sessions. Delivering 99.99% availability for enterprise virtual desktop infrastructure requires solving a complex network engineering problem long before you scale your compute capacity. To eliminate these infrastructure bottlenecks, Nutanix provides a heavily tested framework, the Nutanix Validated Design, or NVD. This diagram maps the 3 NVD layers. At the bottom is the physical underlay, compute, networking, and storage hardware. Next, the Nutanix AHV hypervisor virtualizes those resources. Finally, the top overlay contains the Omnissa Horizon components managing the end-user desktop sessions. That top Horizon layer will only remain stable if the physical networking layer beneath it adheres to strict pre-validated configuration rules. Before running a single physical cable, you must draw strict logical boundaries across the environment to contain potential failure domains. Mixing your control plane infrastructure with user workload virtual machines creates a severe risk. A sudden spike in user activity could starve the management services of memory or CPU, taking down the entire environment. To prevent this, the NVD dictates a dedicated 4-node management cluster. This isolated block hosts only the critical control services: Prism Central, Active Directory, SQL databases, and the Horizon connection servers. Right next to it sits a separate, much larger workload cluster. This block is dedicated exclusively to hosting the Windows 11 virtual desktops. If 1,000 users log in simultaneously and trigger a massive boot storm, the resulting resource drain is entirely contained within the workload cluster. The management cluster remains untouched and fully responsive. By architecturally isolating the control plane from the user plane, you mathematically limit the blast radius of localized failures and protect core routing logic. Traditional 3-tier hierarchical networks, using core, aggregation, and access switches, introduce inherent latency. They source traffic up and down a vertical chain, which buckles under the heavy east-west storage traffic generated by hyperconverged nodes. This schematic details the mandatory solution required by the NVD, a non-blocking leaf-spine network topology. At the rack level, we require 2 top-of-rack, large buffer 25 gigabit leaf switches. Positioned above the leaves are the spine switches. Notice that the leaf switches do not connect to each other for data routing. Instead, every leaf connects directly to every spine. If data needs to travel from a node on the far left to a node on the far right, it goes up to the leaf, up to the spine, down to the next leaf, and into the target node. There will never be more than 3 switches between any 2 Nutanix nodes in the same cluster. The leaf-spine architecture natively flattens the network. It ensures every node is mathematically equidistant, eliminating the central choke points found in older network designs. Looking at the lower half of the schematic, we configure physical cables to prevent blocking redundant ports. Every node cross-connects to both leaf switches via 10 or 25 gigabit links. On the host node side, we enable LACP, the Link Aggregation Control Protocol, on the virtual switches to bundle these connections into a single logical link. On the hardware switch side, we configure MLAG, or Multichassis Link Aggregation Group, across the 2 leaf switches. This provides active-active bandwidth and ensures instant failover if one switch completely loses power. Moving up to the leaf-to-spine uplinks, these connections require 40 or 100 gigabit capacities. Those uplinks are governed by a strict scaling rule. You must configure the bandwidth to ensure network oversubscription never exceeds a 1:2 ratio. Next, we separate the traffic types using VLAN tagging. The controller VM and the AHV hypervisor management traffic must sit on native, untagged VLANs on the server-facing ports. The guest workloads, the actual Windows desktops, must be routed across explicitly tagged VLANs, ensuring user data never bleeds into the hypervisor management streams. Implementing MLAG, LACP, and strict oversubscription limits ensures that a severed cable, a dead port, or an entirely failed switch will route traffic instantly, keeping the user's desktop session active without a single dropped packet. Once the baseline network is configured, you have to scale it to handle thousands of users without breaking your oversubscription ratios. To manage growth, the NVD utilizes a workload cluster building block. You start with 4 nodes and expand linearly, node by node. However, you must stop expanding when you hit exactly 16 nodes per block. Those 16 nodes provide 15 usable nodes with n+1 failure redundancy. Running at optimal density, that specific block delivers exactly 1,500 virtual machines. If your enterprise grows from 1,500 to 3,000 users, you do not force more nodes into the existing cluster. Instead, you deploy a completely new, identical 16-node cluster block alongside the first one. Capping the cluster size guarantees that the internal east-west storage traffic never outgrows the capacity of the dual-rack leaf-spine underlay. Your scaling becomes entirely predictable. To reach the target capacity of 5,000 highly available users, you deploy these maximum-scale workload blocks across 2 separate availability zones. For the active-active clustering to function, these 2 data centers must be geographically close enough to maintain less than 5 milliseconds of round-trip network latency. This diagram shows the cross-site architecture. The individual Prism central control planes communicate across the 2 sites, applying replication policies to user data and configurations. Over this physical architecture, Omnissa's Cloud Pod architecture overlays across both sites, tying them together into a single logical namespace for the end user. Using global entitlements, the system seamlessly routes those 5,000 users to whichever site has available compute capacity, or instantly redirects them if one entire availability zone experiences a blackout. High availability VDI fails without rigorous underlay engineering. By architecting strict rules from the physical switch ports up through the logical management domains, the Nutanix Validated Design transforms brittle networks into a highly resilient foundation for enterprise and user computing.